My name is Tiankai too. I work at DE Research, and I'll talk about fault-tolerant parallel analysis of millisecond-scale molecular dynamics trajectory. Let me start with a brief introduction to DE Research. We are an independent research laboratory in New York City. We conduct the basic scientific research in the area of computational biochemistry. Sorry about this. And currently, we are involved in two main activities. The first one is the design and implementation of novel algorithms and hardware architectures to significantly improve the performance of molecular dynamics simulation. So for short, I'll just call it MD simulations. And the second one that's closely related to the first objective is to use these new simulation tools to advance the basic research in structural biology and biochemistry, and potentially apply what we learned in the process of drug discovery. We already have built a special purpose supercomputer called Anton, which is shown in the lower left corner. And this is a special purpose supercomputer. It's not an Intel-based system. It's not a commodity cluster. It pretty much cannot do anything else except for MD simulations really, really fast. So on the right side, you see a protein structure. This is just a visualization. This is a downsampled visualization of the first millisecond scale BPTI simulation. BPTI is a protein structure. What you see here, I don't expect you to understand what's going on here, but you can see most of the time the protein structure is just kind of moving around by itself. And from time to time, there's some big conformational change. So these simulation will enable computational chemists to understand a wide variety of biological processes that actually occur on millisecond time scale. So this is millisecond. You think this is a really short period of time, it's only millisecond. The prior state of the art was only on the order of 10 nanoseconds. So this is a significantly longer simulation than previously possible. So there's a set of what we call routine data analysis tools computational chemists actually use to derive insight from the simulation output in order to really do scientific research. So I will explain why I put the double quotes on routine shortly. But this is not an exhaustive list of everything chemists will do, but to give you a sense of the type of analysis they will have to perform on a daily basis, which include the data validation. You look at the data sets coming out of the supercomputer, figure out if there's any corrupted data. Usually this can be done quite simply through checksums. And there's some summary statistics you have to deal with, like RMSD, root mean square distance, of all the frames you have generated with respect to a reference frame. And there's some event detection. Basically, these event detection algorithms are not particularly difficult from a data mining or statistical perspective, but it's really, let's say, chemists have some very good intuition of what's going on in the system. They want to see if it's really happening, so they will structure their analysis to figure out what's going on. And also, there's some data mining, but not a very strong component in the whole analysis stack currently. Some vanilla k-mean clustering and the more sophisticated EM-based precocities analysis. So now let me explain why I put double quotes on routine. If you look at a millisecond scale MD trajectory, the simulation length is 1 millisecond. We don't output every single snapshot of the system. By snapshot, I mean we record the position and the velocities of the atoms of a biomolecular system and store it onto disk. And instead, we downsample the output rate. Let's say in this case, the assumption is we output every 100 picoseconds. So we're talking about 10 million frames. Well, we call each output snapshot a frame. Now, for a typical biomolecular system we simulate, we probably have 25K to 50K atoms. And if we record only the positions and the atoms, it's a tiny amount of data, 24 bytes. So each frame is only 600K. But if you put all these together, it's about 6 terabytes. Usually we have from 2 to 10 terabytes of data out of each single trajectory. So this might not appear to be a very large data set, because if you look at other large-scale PDE simulations where you have billions of degrees of freedom, each snapshot can be 10 gigabyte or even 100 gigabyte, but you probably store 1,000 of those or 5,000 of those large snapshots. So then you really manipulate each large snapshot very carefully. But in this case, if you visualize it, it's a tiny stream of tiny frames, tiny snapshots, but it's a very long trajectory. So if you look at the bottleneck of analyze this data set, assuming you have a reasonably well-configured desktop machine, and assuming you can always sustain 100 megabytes per second disk read bandwidth, it will take about 16 hours to just read 6 terabytes of data. Now, as in Alex's talk yesterday, he mentioned the complexity of analysis algorithm when it comes to large-scale data set. It's also our observation, most effective analysis algorithm probably is linear algorithm or n log n. Square quadratic algorithm seldom works in practice. So the total time of analyzing the single trajectory for a single task is probably on the order of a day or two. Now, you don't really generate the data set and analyze it once. Many times you change a parameter, you explore different aspects of data set. So this is the turnaround time that's unacceptable if you just run it on a single machine. At the very early stage, almost like 5 years ago, we came to the conclusion that sequential data analysis does not have the required computational I/O and memory capability to deal with the trajectory Anton was going to generate. So as a result, we developed a set of infrastructure to support this routine data analysis. So the double quote actually indicates they are not routine once the size of the data set exceeds certain threshold. If you run these analysis on your workstation, got frustrated, you just walk away. We'll never wait for the result to come back. And the rest of the talk is roughly divided into these 3 components, from parallel programming model we support to parallel I/O and fault tolerance. So I will walk you very quickly through how we structure AMD analysis in parallel. The methodology here is applicable to a variety of applications. The particular implementation we did was actually, one version of that was released to the public, but I really want to get the main idea of how we do this analysis in parallel. So on top of this, on the top of the yellow line are the 4 different type of analysis, the routine analysis chemists usually do. And for the programming model, let me give you a simple example. This shows a protein on a membrane. So the green ribbon here, it shows a protein structure that's spanning a membrane. And the red box shows an ion channel. These are potassium ion channel that's actually very important for the regulation of the functionality of the cell. And those red dots are just water molecules. And we're interested in the blue balls that indicate the potassium ions. So let me zoom in this. You'll see this. This is a zoom in of the particular channel we talked about. And it shows the potassium ions because of the potential difference across the membrane are permeating through the channel. If your channel is blocked, you're in big trouble. So these are very important in a biological process. So the ions permeate through. It's not a very difficult problem. So sometimes a water molecule would also go permeate through the channel. Now, just give you a concrete sense. Let's say we have a very short trajectory, only 30 frames, and we are only interested in 2 of the particular ions in the system. And the pink line and the yellow line are just hypothetical position of these 2 atoms at different time steps. Right? It's a time plot. Now, assuming this gray area is the span of the channel, you can see that you run a simulation starting from the blue line, move forward in time. And the yellow curve shows the ion A actually permeates through the channel from the bottom of the channel, and it goes out and comes back in again. And the pink channel, on the other hand, the pink curve shows that ion B originally is in the channel. It's permeate out, come back in again. So it's not really a permeation event, which is defined as an ion going from the bottom of the channel, move around, and exit on the top or the other way around. So this is a transition diagram. You can see, let's say it's a state transition graph. with the initial state, some event takes place, move to the next state. Okay, this is just, there's some interstate dependency when you do this kind of analysis. So if you do this sequentially, the easiest way to do it is just maintain a memory data structure to keep track of all the ions you're interested in. And for the position, when you're reading a new frame, you can retrieve the position of the ions you're interested in. Then you can update the position according to the state diagram I just showed you. And then in ascending order, you can process all the frames and come to the conclusion which ions have permeated through the channel. Now, if you want to do this in parallel, it actually poses an interesting problem because you really have strong interdependency among the frames. You cannot really jump to the second half of the trajectory to figure out what's going on in the trajectory. Right? So you have to look at the current state, then move to the next one. So a different way to look at this analysis process is, if you think of the whole analysis, what you're really doing is you first specify which frames you want to analyze. Let's say every other frames, every 10 frames, or every single frame. And then we can really, what we want to do is, because of the data dependency of between the frames, we are combining data acquisition with data analysis. So the best scenario is assuming we can somehow define the trajectory we want to analyze, basically specifying the frames we want to analyze. And then we somehow allow the system to understand how to retrieve the data, basically the positions of the ions for each frame. And then we can perform a cross-frame data analysis to understand what's going on. So going back to this example, let's say the first thing we want, when we want to analyze the data, we want to analyze every other frame in the trajectory. And then for the per-frame data acquisition, we're only interested in the positions of these two ions, A and B. So let's say we have two processors, two nodes, 0 and 1. Hypothetically, we partition the data into two parts, and the P0 responsible for retrieving the position of both ion A and B from time 0 to 14. And node 1 will retrieve the position of both ion A and B from time 16 to 30. Now, in the second stage, if we could somehow group the data that belongs to ion A to one node and the data belong to ion B on another node, then we can do the data analysis embarrassingly parallel. Now, the question is, there's a gap here. We don't know, it's not obvious, at least to computational chemists, after you acquire the data from each frame, how do you do this cross-frame data exchange and communication? So what's missing here is we need to do data distribution among the processes. So chemists are very smart people. They actually are very creative and a very competent programmer, but not all of them are very good parallel programmer. So our goal was to help them to deal with this problem. The inspiration came from Google's MapReduce. I assume many of you know about this model. Basically split the computation into map phase and reduce phase. And the key insight here is how do we bridge the gap between the per-frame data acquisition phase and cross-frame data analysis phase. The way we deal with it is to make use of the key value pair in a somewhat unconventional way. You can think of keys as a categorical name to identify the data set of interest. In this case, we can say it's ion A or ion B. Now, the values, in addition to the positions of the ions, you also need to carry the timestamp from which these positions are retrieved. So in this case, we can use ion ID as the key, and the value will be XYZ, the position of the ion, plus the timestamp from which frame it's retrieved. Now, why do we need the time? Because in the reduced phase, the MapReduce model, the keys, all the values associated with the key will be dedicated to a particular node. You can restore the time series associated with a particular categorical name based on the first timestamp you have already assigned. So this is the step where in the cross-frame data analysis, you can reconstruct the time series without a heroic effort. So all the information is contained there. So we have, HiMach was implemented about 4 years ago to provide a MapReduce style library, which surprisingly was requested by the computational chemists. They thought this model would allow them to manipulate the data and reason about the algorithm more effectively. Though at the very beginning, computer science group resisted the idea. The basic argument was, you're a computational chemist, you're going to do a lot of linear algebra calculation. There were high-quality MPI packages already out there. Why do you want to use MapReduce? But after a lot of discussion, we come to the conclusion MapReduce did have its merit in terms of the clear split between the I/O logic from the algorithm logic. And we built this library as MPI-based library. Basically, it's similar to what Michael talked about this morning. It's implemented on top of MPI. You run a HiMach job on a compute cluster, and you can use MapReduce style calculation to structure code, but in the reduce phase, after data have been retrieved, you can actually roll back to MPI calculation. So think of map phase become data acquisition phase. Reduce phase becomes computation and communication intensive phase. So I won't be able to give you the breakdown of performance, but roughly it's a 2 order of magnitude improvement on 512 cores versus a single core performance. Now, second problem is traditionally I/O has been the bottleneck for both simulation code and the data analysis code. And this is a very typical and traditional I/O infrastructure. In the bottom, you have the Anton supercomputer, and FE nodes represent front-end nodes, and you store data in file servers. In our case, we use enterprise-level NFS servers. And then you run your analysis on a Linux cluster where the analysis node will read the data from the file server. So this could easily become the bottleneck because it's both servicing the read request from the analysis node and servicing the write request from the supercomputer. So in order to solve this problem, we observe a number of characteristics of the MD trajectory. First, we have a large number of very small frames. The second, these are write ones, read many. You don't really change the position of the atoms by yourself. And third is, you can actually distinguish the different frames using the path name of the directory where the frame is stored and the sequence ID in that path name. So it just becomes obvious that this is really amenable to the MapReduce type of processing. You can do the map, disregarding the ordering among the frames, as long as you can uniquely identify each one of those. So the main idea to solve this problem, to solve this I/O problem, was we want to convert the local hard drive on those analysis nodes into a confederate disk cache. They will cache data a user program access and then service directly out of the cache for the follow-up accesses. And we do not want to use a metadata server, which from the storage research community have shown to be hard to get right and usually is a performance bottleneck, and it could be a single point of failure. And the key algorithm we developed was a extended MPI collective operation using bitmaps. It's a distributed consensus problem. The basic idea is you have these analysis nodes that has local disks that could be used as disk cache, and data will be fetched into these caches. And some of the nodes will crash and come back online again. So some of the data will be recached, so there were duplicates and missing data in the system. Now we want to understand, because there's no metadata server keep track of the whereabouts of these frames, we want to understand if I run analysis, which node needs to serve which frame. So there's a consensus protocol implemented using MPI. We implement the system in a library called Zazan. And the yellow box, the yellow fonts indicate the new components introduced into the HiMach framework. So HiMach was still running there, and the Bodhi servers are the cache servers that will talk to the file server and store data and retrieve data from local disk. And the Zazan protocol is the MPI-based protocol to resolve conflicts and identify which nodes need to do what. Sorry, I won't be able to get into detail. This is a very high-level description of the system. And this is a very brief indication of the performance of the system compared to NFS, PVFS2, which is a parallel file system developed at Argonne National Lab, and Hadoop, actually HDFS, with Zazan, this caching system. The yellow bar shows the aggregate read bandwidth on 100 nodes. This set of tests were performed on 100 high-end Linux cluster nodes. NFS didn't perform very well as expected, and Hadoop has problem with small files. This is 1 terabyte data. configured in different number of files of different sizes. But you can see that I just want to deliver the point that actually this caching mechanism worked in practice. And this is the end-to-end performance of HiMach, of a sample HiMach analysis script. You can see the scaling property of the Zazen-based version versus completely memory resident version versus NFS version. So you want to track this green curve, which is the best you could ever achieve, considering all the data access needs. Now, the last part of the technology component is fault tolerance. So at the design phase of HiMach and the Zazen, we actually considered different fault models. The basic assumption was the cluster management software will be able to identify the fail nodes. So those nodes will be excluded from an MPI execution. Now, if during the execution of an MPI job, because HiMach is really an MPI job, any of the nodes crashes, the job is done. It's kicked out. So you just rerun the job using the remaining nodes. So that was the fail-stop model. You can actually identify a failure quickly. And so, but in practice, what we found was the common type of failures actually are related to network file system a lot. So this happened when one of the analysis nodes tried to retrieve a piece of data, a frame, from the file server because of cache miss. And the NFS mount point somehow hangs, never returns. So from the system's perspective, everything was normal. So, but from user perspective, the job just stalled. And because they were at one point enter a collective operation like a global barrier, but some of the nodes are storing on network access. So that led us to realize there's an interplay between the underlying assumption of MPI collaborating processes with the external effect of file access related to NFS mount. So basically, you run into a case where it's not fail-stop. You just hang for no good reason. So here's the main idea how we solve this problem. We want to decouple MPI from disk read operations, and we want to retain the capability of MPI at the reduce phase when we actually encourage chemists to do more computational intensive work. And so to do that, we use a client-server model for the map phase, and converted the original analysis node into a server farm that works as a distributed RPC engine. And we treat these servers as a peer-to-peer network and use consistent hashing to do the frame placement within the system. So one last bullet point, I won't be able to get into details, was we actually allow data reorganization at the application level, which means if you look at a frame, and in most cases, you're only interested in the protein data instead of the water molecules. But when the data come out of the supercomputer, there's no data optimization going on. This is very application specific. Different chemists might be interested in different part of the data. Now, this extension to allow data reorganization actually expose the API of how you want to lay out the data at the storage level to the user code. So you can basically do a column store type of storage structure to improve the performance. And we implement this in a system called Pitstop, which is a really distributed RPC engine. And here on the left side, I showed a small analysis cluster, maybe 40 nodes. On the right is a big Pitstop cluster. Right now we have 75 nodes. We're going through another 100 nodes into the Pitstop farm. And the Pitstop client has all the intelligence. In this case, I just showed a single MPI process K connecting to the Pitstop servers. And the client will actually marshal or encapsulate the running object of the client, ship it to the server, where the server will respect certain protocols of executing the client code. And this happens on all the MPI processes. So in this way, if you think of it, it's really we treat every single MPI process in your communicator group word as a client. So they're farming out these computational requests to all the servers in parallel. Now, the Pitstop client will have strong timeout control. If the server hangs in an NFS mount, as I mentioned earlier, or a server has been overwhelmed because of excess excessive workload, the client will time out and say, this server is no good, I want to pick another one. Now when you pick another server to do the work, it will again ship out the computation to that server. Now if you're interested in the details of how everything works together, we can talk about this offline. But just give a quick overview. We deployed Pitstop as a second generation of the original analysis infrastructure. And in addition to the HiMach batch analysis I described earlier, Pitstop is able to support interactive data exploration. That basically, you can think of your workstation as a client, making parallel connection to all the 100 servers, retrieving data. And it has been able to survive so far various failure modes, in particular NFS mount failures that are occurring on some of the nodes. You basically discard those nodes, pick another one, and move ahead. So to summarize, we have learned over the time after Anton came into production in 2008 that in order to have meaningful interpretation of the molecular dynamics trajectory, there were a number of important issues. In order of importance, actually, I listed it. First is strong scientific intuition. No matter how smart you are as a data miner or statistician, if I just give you the data set, say, figure out what's going on, tell me what the discovery should be, you will not be able to do that. Most of the chemists have worked in the area for more than 20 years or 10 years, so they have a very good intuition of what's going on. And that means they will have a strong say in terms of the selection of the algorithms that must be used to run the analysis. This is the second point. You need to provide efficient and pertinent analysis algorithms. Efficient is very important in terms of algorithm complexity. If it's not feasible, you won't be able to generate the required result. And thirdly, you need to have a fast and scalable implementation because the scale of the data you have to deal with. So all these three are important. While my work falls in between 2 and 3, the scientific intuition part, I have to rely on the computational chemists to come up with that. So roughly, we thought, given the learning experience we have had, the progression from HiMach to Zazen now to Pitstop has enabled our chemists to do more effective data analysis. Thank you very much.